So first, we have to do a bit of boring stuff. We need to set bashrc variables, and I believe in Mac these are now .bash profile. That's right, isn't it?
In Mac, yeah.
Yeah, on Mac this should be. Mac does have a .bashrc, but it should be a dot. You should put these, but where this is the directory of your RMG install.
And these are helpful but not required.
Yeah. Well, they're
they are
otherwise
really
you end up typing a whole lot.
And is it still Cantherm?
Oh, I guess you don't need the Cantherm part.
Yeah, ignore the Cantherm.
You can ignore the Cantherm part. Okay, and if you have that stuff all set up, you can start doing this, which is run the minimal example. You do source activate RMG environment, and then you just do Python. You go into the directory where the minimal example in the example file. If you're in a Git installation, this will be an RMG-pi/example/RMG. First, we're going to look at the database block in the commented example. So the database block defines how where RMG digs its values from, where it gets all the parameters from, where it gets thermal values, where it gets transport, where it gets reaction information, what kinetics families are used, and what kinetics estimator is used. So the thermal libraries, of course, is a list of libraries, of thermodynamic libraries. The order is quite important. They should be in order of how trusted they are, because the first library will take, if it has a value that's in any of the later libraries, the value in the first library will take precedence over all the other ones. So it will take the first essentially when it looks for thermal for a species, it will go through each of these libraries individually, and it will take the first piece of thermal information and come. So you need to be careful to put the most trusted ones first and the less trusted ones further down. Same goes, so then you have the reaction library, which is a list of, most of the same thing. It's a list of libraries of reactions in the order that you trust them in. And then what reaction libraries do is much the same as thermal libraries. However, what seed mechanisms do is a bit different. So a seed mechanism is what you put in the seed mechanism and what you put in the reaction libraries is the exact same names. They're both kinetic libraries, both seed mechanisms and reaction libraries. But seed mechanisms, when you start your RMG run, if you put in a seed mechanism, all that stuff automatically gets added to your run at the beginning of your run. Whereas reaction libraries are just kind of out there and may slowly enter the model if they become important. So if you give if I give H2 to H dot plus H dot, if I have that in a seed mechanism, when I start my run, I will have all the species in it. So I'll have hydrogen and I'll have the hydrogen radical in the model. If I put it in a reaction library, it's possible that I might never have hydrogen, I might never have the hydrogen radical in it. But if it starts to become important, that reaction might become important, it might enter the RMG edge and enter your model. But if it's in a seed mechanism, it forces all of that stuff to be in RMG to begin with. And the distinction between these is quite important, because oftentimes there's some chemistry that you really, particularly the small molecule chemistry, you need to give RMG for like hydrogen and methane chemistry. We usually give RMG that chemistry to begin with before we even start the run, because that makes it stabler. It makes the model grow much more nicely and causes less problems. But also, the nice thing with reaction libraries is that you don't always want to put them in as a seed mechanism, because you usually want, in general, my experience is that it's better to let RMG grow out and find stuff rather than to just give it stuff all at once. And there's a number of, some of the stuff of why that's the case is a bit complicated. I'll talk a little bit more about it. I think there's a lecture on pruning, but I'm going to talk a little bit more about some of the other dynamics that go on when you run RMG. But in general, there's cases for use the seed mechanisms to give RMG everything that it needs to know to start looking at how the things should happen in the mechanism, and then give reaction libraries for it to pull kinetics out that you think are important.
You made just a comment, or maybe you're talking about this, that sometimes you have some species that you really care about, and you are not going to accept any mechanism that doesn't include that species, even even if that species concentration is trivial, part per billion or something, to you, that's the most important species in the whole world. And so then you have, I think, two different ways to force that in.
Yeah, I think that might be the next slide.
Okay, so one of the ways is you could put it in the seed mechanism. So if you put a reaction that involves that species in the seed mechanism, it's going to have that reaction in there, it's going to have that species in there regardless of whether it's numerically significant or not. It's just going to put it in. The common mistake people make is instead of just grabbing what they really care about, they go up to one of these libraries that has 1,000 reactions and says, oh, it has my species in it. Okay, I'll take the whole 1,000. And then the poor computer is starting with 1,000 reactions, and maybe 500 of them are completely unimportant, but it's completely confusing RMG as it gets started, and it makes it spend a lot of time tracking down useless stuff. So only if you care. But if you do care, it's definitely within your rights to control what it does.
Exactly. So there's another option here. So you also have kinetics families. What that does is it sets what kinetics families are available in your run, what types of reactions RMG students happen. And so default mean is essentially the set of families that we think are generally applicable and that generally apply to other things. There's a few that aren't in this, that aren't part of the default. You can also put all if you think those families are important. In general, these other things, you shouldn't, transport libraries, frequency libraries, kinetics depositories, and the kinetics estimator, you generally shouldn't touch. You should keep these as what it has here, or you shouldn't put in a value for them. Because generally, the only other option here is repetitivity, which I don't recommend. And this just includes the training. I think you can also include NIST, but we've found that doesn't work very well. Any questions on the database block? Yeah.
Just to make sure, like for the seed mechanism, for example, you have if I want to specify species in the seed mechanism, so even though later the flux might be very, very small, it will still be included. So it's just
yes.
Okay.
So the seed mechanism at the very beginning of the run, when RMG runs its first simulation, it will have everything in the seed mechanism in it.
Okay.
So if I add a C1 methane mechanism, I will have methane. I will have all the species related to it before RMG even reacts anything to find reaction.
So if you put in H plus H equals H2, and you also put in methane as your starting feed, will you get H atom plus CH4? As a reaction, we'll search to try to find.
If you include it as a seed mechanism?
If I only have H plus H equals H2, that's all my seed mechanism is.
And then you have CH4 as a species?
Yeah.
So if it's over the filter tolerance, it will react though.
And if it's not, it won't?
Yeah.
Okay.
Yeah.
Okay, so initially it would not because I didn't have any H in there initially, but maybe eventually the H builds up enough that I would, okay.
Yeah.
So do we need to include that, let's say I have few reactions, I want to be in the seed mechanism, I make that file, add it to the library folder, or can I give like a path to this is my seed mechanism library?
I would just put it in the kinetics library folder in the same a file in the same format. We have scripts that are going to get talked about later for converting Chemkin files to seed mechanism or to reaction library.
But call it Dumindo library.
Yeah.
Right.
Or yeah, you can just name it and
name
whatever
it,
you
just
name the
little
file.
Okay. Put it in that file.
Whatever you name the
record,
folder will
yeah.
be the name that it will. You can just put it in here and it will work.
Yeah. Don't write it into training reactions or something.
Yeah.
Okay. Unless you're really sure that it's right.
Okay. Okay. Oh, I went on this. So okay. So now this is one. I would say this is one of the most important parts of this lecture, which is deciding what libraries and seed mechanisms to use. And this is probably some of the most important part of any time you start using RMG is what should you give it, what data should you give it to begin with, and how are you causing it to build stuff. And it can be done very, very carefully. It's important to make sure you're providing RMG with kinetics libraries for the stuff it can't estimate properly. And it's also important to make sure you're not using fitted thermokinetics unless it's fitted for exactly the purpose that you're using it for. And these can make very large differences. And so I tried to compile together. This has actually been a huge problem where we get emails from people, and they'd be using these archaic libraries. And we were trying to figure out why that was happening, and then eventually what we realized was that we hadn't updated our examples in quite a long time.
And some of them
So they were all using these ancient thermal libraries, and so people would go in and they'd find the examples and they'd be like, oh, so that's what I'm supposed to be using, which is a huge problem. And so we're trying to fix that, and then this section is part of that. So I went through and I compiled sort of for different applications what our best libraries are for them. So I work mostly on Oxygenate combustion. And so these are sort of my most recommended thermal libraries. Klippenstein-Glarberg 2016 is really good. It's mostly active thermochemical tables, which is like the gold standard right now. Burke H2O2 is quite good. And then these are sort of our calculation libraries of a couple cluster CBS-QB3 and QCI calculations. If FFCM is another good C1 chemistry library, and you could use that if you're using but only if you're using the FFCM kinetics, because I'm pretty sure it's fitted a little bit. For seed mechanisms, I highly recommend this in this particular order, because Burke H2O2 and N2 is a little bit older than this one, and so this one's slightly more up to date. But this one includes some reactions that are important for RMG to get oxidation chemistry properly. Yeah.
Is there a list of the available libraries somewhere online or on the RMG website?
Sorry?
Is there a list of the available libraries on the RMG website?
Yes.
Or is that...
Yeah, if you go to RMG website, go to the database, kinetics libraries, it should list all of these.
Okay.
But this is Burke H2O2 and N2 is important because there's a number of reactions in it that RMG doesn't estimate properly. And then what this seed mechanism does is it provides RMG with sort of the C1 chemistry. It gives it all the stuff to deal with methane really well. And so and then that gives it a chance to sort of grow out. You can also use FFCM. You can swap FFCM for this as well. There are a lot of larger reaction libraries for Oxygenates that can be useful, but most of them are fitted to some extent, or if they aren't fitted, we usually added them to our training depository, so there's not that much use in adding them because we only testing chemistry. But some of them can be helpful in certain situations, but in general, I wouldn't recommend them in general. So for nitrogen, some great thermal libraries. Primary NS that Alon has put together, nitrogen Purin, and then our couple cluster calculations has some nitrogen, and then a really good kinetics library is our primary nitrogen library, and then this one's not too bad. For sulfur, we have these recommended ones. Primary nitrogen sulfur, the sulfur library, a couple of cluster calculations. The kinetics for sulfur are a bit more complicated and depend a bit on the application, but we have a lot of kinetic libraries available in the sulfur folder. And for aromatics, we recommend the static aromatics for thermo, and first to second aromatic ring is a good kinetics library, although aromatics is really hard to work with. So any questions on library choices? This is quite important. So,
Colin, you're doing the low temperature oxidations. Do you have another library that you'd recommend for low temperature?
Not really.
Okay. It's still a research project, is what you're saying?
Yeah.
Okay.
The ones that Matt mentioned are, as far as we know, also suitable. Definitely the thermal ones.
Definitely thermal.
RMG then corrects them empirically to add solvation corrections. But yeah, we don't have any that would specifically be for that purpose.
Okay. Questions? Okay, so now sort of next part of the input file is species definitions, which are essentially just a label, some name for the species, a structure, usually either a SMILES or an adjacency list. It can also be an in sheet. And then this sets whether it's reactive or not, which lets you add nitrogen as an entirely inert species without having to worry about nitrogen reactions. What's nice about this is this lets you anything that you've defined here starts in the RMG model. So there's a specific species you want to add, and you don't have a seed mechanism you want to associate with it. If you just define the species in the input file, it will be included when you start the run, and so RMG will have it. If you set reactive to false, it won't. The species won't be reactive when RMG generates reactions. Okay, so now the reactor block. So we'll start with the simple reactor. So what this lets you define is temperatures, temperature, pressure, and the initial mole fractions. You can also define all of these in ranges, like this here. And it also lets you define termination conditions, which I'm going to talk about in a second. So for the simple reactor, if you just define a single temperature, pressure, single set of mole fractions, in general, what it'll just do is it will simulate at that condition, of that constant temperature and that pressure. It will simulate it until one of the termination conditions occur, and then it will be done. And it will, if it didn't add anything, it will say, okay, this condition is good. And so if that's your only reactor, your RMG job will finish when it says the condition is good. We also have these ranged reactors, which are a little bit more complicated, but you can define the ranges of temperatures, ranges of pressures, and you can also define ranges of initial mole fractions. If you're defining ranges of initial mole fractions, you usually want to define a balanced species, and this is a species that's adjusted to maintain these ranges. So in this case, we defined a balanced species of N2. So N2 is at this concentration, but it will actually as we sample and as we do conditions in here, this will adjust so that the ethane mole fraction is whatever is in this range, and O2 is always at 0.1. N-sims is the number of samples it takes within that space, within that the space of temperatures, pressures, and mole fraction range. This is the liquid reactor, which is just mostly the same. It's a little bit different. You can do the same range stuff can also be defined for the liquid reactor, except you're defining initial concentrations instead, and constant species is particularly that you can define a species that will be constant. Oh yes.
For if you have a range of pressures for which you want to run, you have to define all the ranges, or you should just say the beginning and the end.
Just the beginning and the end. I'll talk about it it's like next slide. Oh, if you're do you have to define all of the pressures and temperatures within the range? And the answer is no. It actually samples throughout the entire space of the range, and I'm going to talk about that in a second. Okay, so ranged sampling reactors. So this is a new thing. I think I built this last March. And essentially what the idea is that instead of setting a bunch of reactors at a specific point, what if we sample over the entire space that we're interested in? And so the way it works is we define a grid over the parameter space. So suppose we just care about temperature and pressure, and we're being really sloppy, so we pick a grid with only 4 points in it. So what it'll do is it will look at past conditions that it ran at within this space. So maybe it did a point here, and it will then it will choose a point randomly of these ones, but it doesn't in a biased way, in a weighted way. So because the point here, it will be much more it's weighed so that this point will be much more likely to be picked than this point, and these points will be kind of somewhat likely to be picked, and then it will draw a sample with ranging on those weights, and based on that, it will pick one of these points. So it'll be most likely to, if we just took one sample here, it'll be most likely to pick this point. Maybe possible to pick this point, possible to pick this point, really unlikely to pick over here. And so it'll pick, so let's say it picks this point, and then after it picks this point, it takes a random sample within a circle around it. And what that allows us to do, especially when you have a much denser grid, is you're actually sampling the entire temperature, pressure, mole fraction space. Any questions on that?
Is this implemented as a convenience function, or is there some information within RMG that you're exchanging between the different thermodynamic points?
So I store run information and use it to bias the pick point. It's also, so.
I guess what I'm asking is, what's the advantage of doing it this way versus if I just wrote a for loop on my own?
Okay. Good question.
To do that?
And the answer is actually that I've been able to show that these make bigger models than if you do it by the for loop approach.
So you're using information from each individual run?
Yes.
And exchanging that in a.
So so like it keeps in memory every run it's ever run, and then the runs that are really far back get way lower and lower as you extend it out. So if it was recently at this point, that means that it biases it more towards this way, but maybe the point before it was over here, so maybe it takes a point over here. But what's more important about this than that is that I've found that it gives you a bigger model, which tells me that consistently a bigger model across all sorts of runs I've run, which makes me inclined to believe that it's not just, well, it is certainly more convenient to write this. I think it's also, I have some evidence to the argument that it samples better, that there's some parts of the chemical space that aren't being sampled if you just pick a bunch of set of points. I'm not exactly, presumably it's some graining, it doesn't matter, but I'm not exactly sure what that graining is. Yeah, good question. So what you can also think about, what's quite important here is setting NSIMs, which is the number of times you sample here, because the one issue with this is that there's a possibility that if you take too few samples, that you'll just randomly pick two points that are really good, and then you're done, and then RMG will complete when you're actually not converged over the whole interval. But the good thing is that setting NSIMs high doesn't really have that much of an expense to your RMG run, because it ends up just being an extra number of simulations you have to run, which is almost, I mean, in most cases, even if you're within a large model, it's maybe an hour. It's a very tiny fraction of your actual run time. So setting it, well, you don't want to set it ridiculously high. You can usually, in my experience, setting it quite high, you can do it with relatively no cost. I'm going to talk about it later. I have a bit better guidelines. There's an RMG Cookbook that I've put together that is basically compiles our knowledge on how to do the practicalities and weird things in dealing with all these runs, and talks a little bit about how to pick NSIMs. But we'll get that to you by the end of the week. So termination criteria is another important thing to think about. So we have three termination criteria. Time, which is essentially that we say, okay, after 40 seconds, the reaction stops. And so then RMG will just run and simulate it up for 40 seconds, and then it will end.
This is 40 seconds of reaction time, not 40 seconds of computer time.
Yeah. And then conversion, which is it simulates out to a specific conversion of one of your initial species. And then rate ratio, which, so Alon probably briefly mentioned that we calculate a characteristic rate to measure how fast the rates are when we're adding stuff to the model. And what rate ratio does is we keep track of the characteristic rate, and we measure, we use that, so we keep track of what the maximum value is, and once we reach a given fraction of the maximum characteristic rate, we assume that whatever event we were tracking, whatever reaction we were having happen is over, and then it terminates. And so what's worth saying is that one of the problems with time, if you do time by itself, is that you usually don't know when the reaction is going to end. And what you can also run into as a problem is that when you run out farther than the reaction happens, your characteristic rate gets very, very small, which means that there's a lot of stuff that can start to become important that isn't really part of your actual reaction system that you care about. And sometimes I've seen situations where that can give you some kind of nut species. Conversion has another problem, which is that when you're running RMG, often at first, it can't get to the conversion you expect it to get to. So if you were to use conversion by itself and you were to set 99% conversion, RMG would, if equilibrium for RMG at the time when you're running it is 60% conversion, it may not convert at all. It may not ever it may never terminate. And so it's really important to not use conversion by itself. Usually, rate ratio usually works pretty well by itself. There's theoretically situations where we think it wouldn't work, but we haven't found any of those yet. Time and conversion are usually together, usually isn't too bad. Rate ratio is a new one that I worked with that works reasonably well works pretty well by itself. These ones should usually be paired with another one. Termination criterion if you're going to use them. Any questions on termination criteria? Okay. Okay, so then there's the simulator block, which is quite simple. It just sets the solver absolute and relative tolerances. I'm going to talk a little bit more about, if you're around for the simulations lecture tomorrow, I'm going to talk a bit more about what to choose for these. But you can set the sensitivity tolerances and the concentration tolerances separately. So now the more interesting block. So this is sort of the model block. And what this does is it tells you, this controls a lot of the parameters related to whether RMG adds stuff or doesn't add stuff. So the tolerance move to core is the most important parameter here. And that's the parameter, that's the fraction of the characteristic flux at which when a species flux reaches that level, it will get added to the model. And then there are interrupt tolerances, tolerance interrupt simulation. And once the ratio between a species rate and the characteristic rate reaches this level, then the simulation will just the RMG run will terminate, and it will be done. And some of you are probably thinking, well, why don't you just terminate when you add the thing? And there are two reasons to not terminate when you add the thing. And you're usually some of them we're gonna talk about both of them in a bit more detail on the pruning lecture. In general, there are reasons that you'd like to finish the simulation. One reason is that you may want to add more than one object at a time, and there's some benefits to doing that. Another reason is if you want to prune, it's quite important to finish the simulation. But I'll talk about that in a bit more detail later. Most of these are pruning or surface parameters down here that you don't need to worry about now. But there's this is where all the stuff happens, that stuff happens. So then there's the quantum mechanics block. So this works. It has on-the-fly semi-empirical calculations. Usually only run for non-radical cyclics. We usually don't use this very much anymore. It's not mostly because it usually group additivity is better. But theoretically, there are some molecules that this might be worth doing for. But we're starting to move towards higher level quantum calculations and trying to integrate those around instead. So the machine learning estimator block, so this defines which species the machine learning thermal estimator will be used for. Colin has provided a wide variety of options for you to set ranges for this, to set uncertainty cutoff, whether it's for cyclics or not. Mid-cycle overlap, I assume, is related to fused ring stuff?
Yeah. Okay.
And then minimum of these sorts of ones. Name just refers to the weights you're using in the database. What's this one mean?
Currently, the only option is main.
No, I mean thermo.
Oh, thermo. Well, in the future, we might include kinetics or something, but for now, only thermo is available.
Okay. You have plans?
Max's idea.
Okay, so and this is the pressure dependence block. So Professor Green will be talking about this later. And so we actually have 3 different methods for this. Modified strong collision, reservoir state, and chemically significant eigenvalues. But usually we use modified strong collision because it's the most robust. Temperatures is the temperature range for that you want your kinetics to be valid. The temperature and pressure ranges you want your kinetics to be valid for, and the number of samples that you want to take for the polynomial. Max, and then these are related to the pressure dependence algorithm. These are related to the, the points you take are related to the interpolation. These are related to the pressure dependence atoms. But the important one that I'll talk about here is maximum atoms, which is how many so in general, if you have a large enough molecule, the change that pressure dependence causes starts to go. You can neglect the pressure dependence. And so what this lets you do is say, I think usually we set it to about 15 atoms. And what that means is that if your molecule is larger than 15 atoms, it won't calculate pressure dependence for it. Oh, I should have taken this out. Actually, our PDEF's a lot more robust than it used to be. PDEF works quite well now. It used to have a high failure rate, but Max did some stuff that improved that. Okay, so here is options. And what options does is it tells RMG what we want to print out when the run finishes. So there's a couple. These are related to saving seed mechanisms, which are essentially just a reaction library of the model you just built, which makes it possible to reload restart runs. We do have an actual restart file, but I wouldn't recommend it. In my experience with it is it takes a really, really long time to make. It slows down your run. And sometimes your run just fails inside the restart file, which means you can't restart it. Output HTML is quite nice. I'll show some of that in a second. Or actually, you'll be able to look at it in a second. Generate plots is not usually something you don't want. It sounds really nice, but it's actually just RMG statistics. Save simulation profiles saves the plots of the RMG run, so the mole fractions of the species. Save edge species you usually don't want. Yeah, and those ones aren't usually not that important. Those 3 are the most important parameters. So generated species constraint is a really important block. So it lets you set molecule size restrictions on the kinds of molecules that can be generated. In particular, maximum radical electrons is one you want to take a look at. Usually you don't want to set this greater than 2 unless you have the nitrogen triad can be important in some situations. That's kind of the exception to the rule. Sometimes you could theoretically set it to 1, but it might be a bit risky. And these molecule size restrictions can have a very significant impact on your model. So you want to consider what sorts of reactions you expect to happen in your system carefully, and what stuff you're concerned about catching. Okay, so now we're going to take a look at RMG output. So now you all learned how to launch your RMG jobs. So now we go to the super minimal example, which is this, and then do this. Python $IRMG input.py. Sorry, that's I'll change that. That's how it is on my computer. Sorry. Go into the input file and change. Go and generate seed each iteration and set it to true in the options block, and then run the RMG job.
This is assuming we've already run it successfully.
Or no, change this in the options block and then run it.
Okay, but you're assuming we've already run this
No.
script?
No.
No? Oh.
No, not at all. Because we're going to change the input file, we're going to run it. This one's really short, like 8 seconds. Or, okay, maybe not 8 seconds, like So first part of output is the RMG log. The RMG log essentially just tells you how species and reactions got generated and how, over the course of the run, how it got added to the model. It also gives a little bit of debugging information and some error information related to if things went wrong during your run. The Chemkin files are right now are where we store most of the most comprehensive information. It has all the thermo in Chemkin format, thermodynamics information, how it's calculated, where it came from, kinetics, how the family library came from, how it was estimated in the rate tree, and then also a species dictionary with the molecular structures for every species.
Wait, sorry, and what's it called? Is that output.html?
Chemsub-annotated.inp. It's in the Chemkin
Under the Chemkin folder.
It's in the Chemkin folder. Chemkin folder has all of the RMG, all of the Chemkin files generated during the run, and one species dictionary. And then there's also another output, which is seed mechanisms that are human readable. They're a little bit harder to read than the Chemkin file. Some ability to restart jobs. And then the simulation plots, you can look at the actual plots of what RMG simulated. And it's at each iteration, which sometimes is, or actually not at each iteration, I don't think at each iteration. But you can use that to check that all the major species that you're seeing are reasonable. And then HTML files, which are particularly useful because they look really nice. And they show all the species and reactions in terms of chemical structures, much easier to read. It's easy to generate them, but sometimes if you're doing a large mechanism, it's really, really hard to display them in your browser. And so one nice trick to use is to delete copy your Chemkin file to a new file, and then delete all the reactions. And then you can just look at the species, which is usually enough information, and that loads a lot better than loading all the reactions too. Okay, so now let's So here's the Chemkin file, and you should be able to find this in your example. Take a look at it. As you can see here, it's changing as the RMG run's progressing. And so we've got just kind of the elements and then the species. So over here, commented off is not often it's the smiles of the species. But it's actually the name of the species in RMG, which if it has a name in a thermal library, it will usually use that name rather than the smile string. But this is very useful for being able to tell what species are, because Chemkin has a number of restrictions on the naming conventions. And so there's certain things that can't be named that we would rather use as names because they're more easy to read. It's easy to read if it's a smile string. But the names are up here. And then we have all the thermochemistry here, which some of it's from the primary thermal library. So if it's from a thermal library, it'll just say it just like that. But here you have a case of where it's estimated from group additivity. So this is the HO2 radical. And so what it did here was it took one group for one of the O's, or two of the same group, because the O's with all the hydrogens on the O's both look identical. So So they both are assigned the same thermodynamic group, and then we add an HBI correction to take one of the hydrogens off of it. And as we'd expect, we see that the H2O2 is the same except without the HBI correction. And then here we get some reactions. And so up here, just a warning, this example is horrible. This is not a model you would ever want to use for anything. It's just an example that runs really, really fast. It's a good example of running RMG, and it's small. So these are not how we would, if you were actually going to estimate these, you wouldn't use it with RMG's trees, you'd use it with a library. But in this example, we asked RMG's trees to estimate the radical recombination between two hydrogens, and it obliged us. Oh, we actually have a good reaction in it. So maybe this isn't so bad of an estimate. But we can see that right here. So it tells us first where the template is from. So we know this is from the R recombination family. And it tells us exactly what training reaction it matched. In this case, what it's saying is that it matched an exact training reaction. So this is actually separate from the tree. It dug through the depository and said, this reaction is exactly the same, so we're going to use that.
But this is the high pressure limit.
Yes, it's a high pressure limit.
Yeah, whereas in reality, you get
Yes.
equalization high pressure limit, you need like 1,000 atmospheres.
Yeah.
It's not realistic.
And what it also tells you is it tells you what rate coordinate it matches, which isn't that relevant here because it just used the reaction. But that's useful to know if you need to dig through the trees to find stuff. And then here, let me see. Here, okay. So here's one that didn't match a reaction. So in this one, what it did was it estimated using an average of two templates. So what it did was it went down to this rate rule, this coordinate in the tree, and then it went and it looks. What it does is essentially it just steps out in the tree in different ways. And what it found was there were two locations in the tree where there were data that were one distance away. So in this case, it went up from HRAD to YRAD, and in this case, it stayed at HRAD, but it moved up from H2O2 to this. And because those were the same distance, it just took the average of those two. The Euclidean distance of the averages was 1, because it went up 1 on this dimension to this one, and up 1 on this dimension to this one. It also multiplies by the path degeneracy to get the degeneracy properly correct. And here's another average. So here's another one. This is a little bit different. In this case, it only found one template that was close to it. It was one distance away. So in this case, rather than an average, it just estimated it as the O primary rad O birad recombination, as an O rad O birad recombination by moving in this dimension, moving up 1, giving you Euclidean distance 1. Okay. Any questions about the Chemkin file output? Okay. So the species dictionary looks like this. It's quite short for this one, but it's essentially just the name of the species and then the adjacency list format for everything. It's not too complicated. Okay, so let's back up a little bit and open up the HTML, which I guess you don't get the full flow of it from the super minimal example because it doesn't have all the crazy structures that you get when you run other models. But if was a complicated structure, it would give you the organic structure, which is a lot nicer to look at than just a name or something. But what this does give you is it gives you the thermo parameters, so the H at 298, S at 298, and then the CPs at a variety of temperatures. We also have the capability to take two RMG mechanisms and compare them. And what you can do with that is that, so maybe you ran something with one thermal library and something with a different thermal library, and what it will do, I think it's called diff models, I believe the script is called diff models, and it'll generate an HTML which will have all of the species, and then it will do a comparison. It will tell you whether the thermal was really close, but not quite the same, if they were very different, and stuff like that. This also has all of the reactions in it as well. And it references to the RMG website. I didn't know it did that. Cool. You can also adjust what's shown here. Provide the heat of reaction, chemical strength, and kinetics. Give you more information, but that's quite a nice format to look at stuff in. And so the reaction seed is just another reaction library that's generated that's identical to it, just like what you've already seen. And here's the simulation plot. So what this does, this is because we saved the simulation profiles. So this gives you all the plots of all the species. So while most of them are just down here, we can clearly see H2 and O2 and water. You can see that. It also includes the CSV for all of these, and it actually saves every simulation. Although some of the early ones probably aren't worth looking at. And it saves a CSV that has all the data for each of those simulations. And RMG can also run sensitivity analysis. So if you turn that on, you'll also get these plots that give you the sensitivity, the top. I believe it's the top 10, but if stuff's below, you set a threshold. If stuff's below the threshold, it won't include it. For sensitivity to thermo and sensitivity to rates. And this is for just hydrogen, because then you can tell it to give sensitivities to whatever you want. Any other questions on output?
Where can you get the sensitivity?
So for the sensitivities, they won't be in yours right now because we didn't run it with sensitivities. But what you do is when you define the reactor, you can set this to a list of names of species you want sensitivities for. And what the sensitivities actually are the maximum sensitivity over the entire simulation. The max that occurred, the max local sensitivity that occurs. And the sensitivity threshold is the level at which, if it's above this, it will include it in the plot. Any questions? So the RMG Cookbook, there's a lot of potential pitfalls dealing with this. I've tried to circumvent as many of them as possible, but RMG can be a bit complicated sometimes. So we're going to provide you, I have essentially 8 pages of information that we've sort of accumulated on running RMG and what sorts of problems can occur when you do certain things in RMG. So those, in general, has a guide for what you should set RMG parameters to, how you should select what they are, based on practical experience, and some of the better explanations of things that happen. and this has a lot of potential to save you debugging time, so you should take a look at it before you run your first big real job. So there are a number of more specific RMG run features. So one is run concatenation, so in some cases you might want to have RMG behave a little bit differently in most of your run than in the first, say, maybe 50 species of your run. And in that case, you can add simulator and model blocks. And when you add more simulator and model blocks, what it does is it puts them all on a list and it does them iteratively. So it will run through the first model block, which you might actually, what you can set there is you can set in that model block that you want to terminate after 50 species, say. And then it will run that model block until that model block's conditions are satisfied. And then it will start the next model block. Or change to those, and then all those parameters get changed to the next model block until it finishes. Another feature that's sort of something that's I have some evidence that this is a quite useful and quite a good thing to do for your model. That instead of taking one species every simulation you run, take multiple species at a time. And what you can do with this is what you do is instead you set your tolerance that you're running at, and then you set the tolerance interrupt simulation into something farther out, so that it simulates past the time when it adds the first species, say. And once it's done that, then that will allow it to just add more species. What you do is you set maximum obs per iter, which is the number of objects it's allowed to take during a given simulation run. And so if you set this to 5, it can add, potentially the simulation could add 5 new species to your model. Terminate at max objects essentially just lets, if you set it to true, when you reach the maximum that you've requested, it will terminate. And there are reasons why you wouldn't want to, if you're pruning, you wouldn't want to do this. So now we're going to run one last example. So go to the minimal staged input file and change maximum species in the second model block in that file to 25, and then run the example. This is the RMG Cookbook. So what we have here is we have a little bit of information on how to, specifically on each sort of aspect of your RMG job. So here's a bunch of block on reactors, what to set concentrations to, what happens when you run, try to combine different RMG runs, sampling reactors, anchoring, all the different termination criteria, seeding libraries, run concatenation, model setting stuff related to pruning and surface algorithm, and then the options, generated species constraints, what to set everything to, pressureDependence, and although some of this I can fix very scripted. And then also analysis for related to errors. One of the things that's worth talking about is what's useful to look at in those simulation profiles is that sometimes RMG will have trouble breaking down a particular species, and so there'll be one species that's sitting there in your model that gets created but doesn't really get destroyed, even though it should be getting destroyed. And sometimes when that happens, you need to do something about it. One thing you can do is you can make stuff a bit more concentrated, and that tends to help a little bit. You can also run a job for that species' own oxidation or whatever, or pyrolysis itself. But it's something that's important to catch. It happens every once in a while. If you're getting a DAS pack error, usually that's because your thermochemistry is horrible. And you should always check that your products and your major species are all what you expect and that they're reasonable. And then pathway analysis is really important. I'll talk a little bit more about that in the simulations lecture. Yeah. Okay. So the only real takeaway from this one was just that we were able to change between these stages, which changes the tolerances at which it reacts, and at which it starts taking species, which gives you some control over how the run takes place. And if there's stuff that's happening early in the run that you want to prevent it from happening, this provides you with ways to prevent that. That's all I have. Other than that, that's all that I have for this lecture. So.
Yeah, maybe I'll just make a comment. If the examples we've done so far have kind of small molecules in them, when the molecules get bigger, the number of sites that each molecule can react at gets very large. And if you do kind of a breadth first search, where you try to find all the reactions of all the primary sites and then all the initial reactions of all those initial products, it gets very, very broad very fast, and you tend not to get very deep. You don't get very far towards your final products because you just overwhelm the computer by making so much stuff. And in cases like that, you might want to turn off certain reaction families. You might want to use tighter tolerances to begin with. There's like all kinds of tricks you could use to try to help coax the computer to find the main pathway. And I guess maybe that's a general comment, is that RMG has an algorithm that's trying to find all the important stuff. It doesn't mean it's really going to find all the important stuff that easily. If you set the tolerances really tight and you run it for a million years, it'll probably find all the important stuff. But you usually want an answer like by the end of the day, and your computer's going to run out of memory if you just try to brute force it. And so a lot of times in bigger molecules especially, if you can be clever to try to help coax it to find important stuff sooner, then its subsequent estimates of how important things are more accurate the more of the important chemistry is already in the model. So it's like the more you can kind of help it along at the very beginning to get in the direction. However, if you don't know what you're doing and you help it along in a wrong direction, you can give it a lot of trouble. So this is a two-edged sword. You really have to know what you're doing, but you'll see. I mean, a lot of times you just try first and just ask RMG to run by itself, and then if you're not satisfied, then you start resorting to human intervention to try to help it out.
So speaking of brute force, that's sort of my favorite algorithm.
Brute force, yeah.
How far does it get you in terms of like the scaling of the actual RMG and in terms of memory and compute? How much rope do you have to hang yourself with until it's just you have to be clever, you have to have some
so
knowledge, you have
I
to
think
hear it.
if you run things up to like 100,000 species in the edge, or a million reactions considered in the edge, that's just getting around there. It starts really starting to die.
16 gigs is about 100,000 XPP.
Yeah.
Well, we'll talk about the pruning thing is.
There's some ways to try to beat this, but it's like if you're going to get to scales where you expect 100,000 species would all be eligible to react pretty easily, you're likely to have trouble because the poor computer is going to have trouble sorting through the million reactions of 100,000 species.
Okay. So you find yourself more RAM constrained or compute?
Originally it was always RAM constrained, and then we worked on the algorithms a lot and shifted it more to being CPU constrained.
Thank you.
Yeah, and so now we're trying to parallelize RMG because we're CPU constrained, but it's a very tricky program, so it's not trivial to parallelize it.
I remember there's some of these jobs that I ran out and I did the timing for it, and there are like 4 or 5 different things that are all consuming about the same amount of compute time. And
it's very frustrating.
Yeah. Parallelize it pretty well.